Yo, what's up, guys? Welcome back. Episode 81. Yeah. Uh, 81. We're gonna check out our Pokemon of the day. Pokemon 81. We got a Magnemite. Hang on, let me gotta quickly respond to this text. Okay. Let's check out our sound. Oh. Boop. One more. There's my sound, bro. There's my sound. But yeah, we're going to take a look at some more problems today. Just a little announcement. I created a Discord. So if there's anyone that that keeps watching these videos and wants to stay in touch and message me, or just maybe create a community on the Discord, you guys are more than welcome to join. It's in the description of the link tree, and also in the link tree links in the bio of the channel as well, I think. So but yeah, let's get straight into some more problems today. I did look at this one a little early today. We're not going to attempt this. I think what we're just going to do is we're going to keep we're going to check out our powerful study program. Maybe we can finish off a couple more of these binary tree problems. There's a few more that we're missing. We got part sum 3, part sum 2. I'm going to do these constructing the order of pre-order and post-order traversal. Let's take a look at these. Given two integer arrays, pre-order and post-order, where pre-order is a pre-order traversal of a binary tree of distinct values and post-order is the post-order traversal of the same tree, reconstruct and return the binary tree. Okay. Pre-order and post-order. Construct binary tree from pre-order and post-order traversal. So, given two integer arrays, pre-order and post-order, where pre-order is a pre-order traversal of a binary tree of distinct values, and the post-order is a post-order traversal of the same tree, reconstruct and return the binary tree. So why do we need to do both? That's what I'm confused about. We mark this hard. Yeah, probably not entry. My intuition isn't there. I don't think I'm really kind of understanding this problem, right? I mean, it is a pretty straightforward problem where, like, constructing a binary tree from post-order traversal. My friend is calling me on pre-order and post-order traversal. Let me send the problem. Given the pre-order and post-order traversal of binary tree, you need to construct the original tree from these traversals. I think this is the binary tree, right? And then we did a pre-order traversal on this one. And then this is the post-order, I think. Root left 2 4 5 3 6 7. We go root left right. Postal would be, is it right left root or left right root? So we go left first. Wouldn't this be four five two? All right, so we're given, I think, okay. So we're given this, but we want to turn it into a binary tree. 1, 2, 3, 4, 5, 6, 7. I think. I'm a little confused with the array. Yeah. I'm actually gonna watch a video on this one.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, construct binary tree from pre-order and post-order traversal. So first, before we get into it, I want to mention this is very similar to another problem that we have solved. And yes, of course, it is a Leetcode 150 problem. So if you go to the tree section, it is this problem, construct binary tree from pre-order and post-order traversal. I would recommend understanding this one before you get into today's problem. So if you look at the solution.
Okay, let's do that one then. Let's do, I think because that's in our list. I think it was this one, I think.
This is dopamine. This is cheap dopamine, but so is this, and this, and these.
Hey everyone, welcome back, and let's write some more.
Okay, same thing. So given two trees, pre-order and in-order, where pre-order is a post-order traversal of a binary tree, and in-order is the in-order. Take a look.
Code today. So today let's solve a pretty fun problem. Construct a binary tree from a pre-order and in-order traversal. So we're actually given two integer arrays representing 1, the pre-order traversal, and 2, the in-order traversal of a binary tree. And our goal is to take these two traversals and
I'm gonna quickly send out an email really quick. I totally forgot to send this. Oh my gosh, dude. Okay.
The orderings of those nodes, and then reconstruct basically the original binary tree that the traversals are from. And it is technically possible. These two traversals have all the information we need. We just need to take that information and then deconstruct it and then reconstruct this binary tree from those. So just to verify it, let's go through this tree and actually do the pre-order traversal first of all. So first, we know pre-order traversal is you start at the root and then you process the current node, then you do the left subtree, then you do the right subtree, right? So let's just do the pre-order traversal. So we're starting at the root. We do the root node first. That's how pre-order works. So then we get a 3. Next, we're gonna go to the left subtree and then do pre-order traversal on that left subtree. We see 9, right? So we're gonna add 9 to our pre-order traversal, and it doesn't have any children, so we're actually done with 9. We're done with 3. Now it's time to do the right subtree in pre-order traversal. So we start at 20. Add 20 to our pre-order, go left, we see 15, add 15 to the pre-order. 15 doesn't have any children. Now we go to the right subtree, 7, so add 7, it's our last node, to the pre-order traversal, right? And this actually, take a look at this, take a look at all the values, it matches exactly with the input, so this is the pre-order traversal. Now let's just validate the in-order traversal as well. In-order traversal is we start at the root, right? We take care of the entire left subtree first, then we take care of the root node, and then we take care of the right subtree with in-order traversal. That's the general order, so let's validate the in-order traversal of this tree. So we're starting at 1, we're starting at the root 3, but we're not going to add 3 yet. First, we're going to do the left subtree. We see we have a 9. The 9 does not have any left or right children, so now we can add that 9 to our in-order traversal. Remember, we're doing this in order, left to right. We go back up to the root. Now we can process the root. We can take 3 and add it to the in-order traversal. And now we're going to do the entire right subtree. So we get to 20, but we're going to wait for 20. We're going to first do the left subtree, 15. 15 is the only value here, so it doesn't have any children. Add 15 to the in-order traversal. Now we can add 20 because we've done the left subtree. 20 is added, and then last we go to the right subtree, only one value, 7. Let's add that 7 to our in-order traversal. Now let's take a look at these 5 values. Notice how they are the exact same 5 values in the exact same order as that in-order traversal that we were given. So we can see that what they gave us was correct, but now the question remains, how can we actually take these two arrays, these two traversals, and construct this tree? Well, it's definitely possible. Let me show you how to do that right now. So I just want to let you know that there's actually two main facts that we're going to be using to construct this tree. So the first fact is that the first value in pre-order traversal is always going to be the root, right? We remember when we do pre-order traversal, right? We're always processing the root first. So if I was taking the pre-order traversal that we're given, right, we remember this is the pre-order traversal that we're given. The first value in pre-order traversal is always
pre-order, right? What we do?
Going to be the root. So this is the first value, 3. It's guaranteed to be the root because that's how pre-order traversal works. The first value in pre-order traversal is always the root node. Now we don't know about the rest of these, right? But we can recursively construct now the left subtree and the right subtree, right? We're done with this 3, right? Now our goal is to reconstruct the left subtree. Hey, lucky for us, the first value here is always going to be the root of the left subtree, right? Because that's how pre-order traversal works, right? So that's one thing that we're going to use. The first value is always going to be the root, and then we can take the sublist, right? We can remove the 3. We don't need to look at it anymore. Then we take the sublist, and then basically we're going to do this recursively. That's what I'm telling you. Okay, we can construct the root, but we need more information than that, right? And then let's say we're done looking at this 3 now. I want to take this array, right? And I want to know which values are going to go in the left subtree and which are going to go in the right subtree. From looking at the actual tree itself, we know the answer, right? We know that this is where we're going to cut our list, right? The 9 is going in the left subtree, right? These 3 values are going in the right subtree. But how can we determine that? Well, that's what we need our in-order traversal array for. Okay, so now let's take a look at the input array we're given for the in-order traversal. And by the way, let me just mention that every value in the traversal is guaranteed to be unique. That's true for both of the traversals, the in-order and the pre-order. Every value is going to be unique because every value in the tree is going to be unique. But okay, so far we know that this first value 3 is going to be the root, right? So now let's find 3, right? We know 3 is the root, right? So we removed it from our first list basically, right? But now let's find it in our in-order list. We find it's right over here. 3 is in this index, right? So we know we don't need this 3 anymore, right? We already created that node. But so now what does this in-order array tell us? Notice how this is convenient for us. Every value to the left of the 3 that we just created the root from, every value over here, which is only 9, is going to go in the left subtree, and every value to the right of 3 is going to go in the right subtree. That's really convenient for us. Why is this the case? Because that's basically the purpose of in-order traversal, right? It guarantees that we're going to go through the tree in order, right? From left to right, basically. Right, so if we see the 3 here, and this is the position in the array, we know everything here is going to be in the left subtree, everything here is going to be in the right subtree. That's what it tells us. This is really convenient for us because we can count it, right? We can see there's exactly one value that's going to go in the left subtree, and there's exactly 3 values that are going to go in the right subtree. So what we can do is we can take the remainder of the pre-order array and then partition it, right? Partition it over here because we know 1 value is going to go in the left subtree and 3 values are going to go in the right subtree. So that's what we're doing, and we're going to continue this, right? So now let's and by the way, in the code, we're going to do this recursively. Let's create the left subtree. We know that, okay, this is the in-order portion, right? And this is how we're going to partition it from pre-order, right? We see this is the array to create the left subtree. The thing here is, notice how this is size 1, right? There's only 1 value here and there's only 1 value here, right? That tells us that the subtree we're creating is only going to have 1 node in it, right? So 9 is the only node in the left subtree. So we're going to create that node, put the value there, and now we're basically done with this left subtree, obviously, because there's no more there's no more nodes left in this general area, right? These values are reserved for the right subtree. This is reserved for the right subtree. Okay, so now we're looking at the pre-order portion, right? There's 3 values, just like in the in-order portion. And remember, how are we going to create the root node of this subtree now? We always take the first value in pre-order traversal. It's 20, right? The value is 20. So we're going to take this value 20. We don't need it anymore because we're going to create a node from that value. And so now we need to know which values are going to go in the left subtree and which are going to go in the right subtree. We know by finding 20, right? 20 is the value. Let's find 20 in our in-order traversal. It's over here. By the way, in the code, I'm going to be calling the index of this mid. So M for mid. We find the index of 20, right? We know we don't need 20 anymore, so we can get rid of it, right? We see that there's one value on the left of 20, and there's one value on the right of 20. This tells us that one value is going to go in the left subtree and one value is going to go in the right subtree, right? Just like we have over here. So now let's construct that left subtree. We know it's going to be exactly size 1 from looking over here. So we take this 15, right? Now our job is to recursively create the left subtree. We're going to take this 15 since it's the first value in the subarray for pre-order, right? We know that it's going to be the root of the current subtree we're at. So let's get rid of this 15. Let's create that node, right? 15 over here is going to be a node. And there's no more values left in this subtree because we know it's only going to be size 1. Okay, now we're creating the right subtree. We know that there's only one value in the right subtree from looking over here. And since there's only one value left in general, it's a 7. We can make a node from it. And then we're done. We know we're done because we've basically gotten rid of every single value in our arrays, pre-order and in order. So using these two arrays, we were able to create our tree correctly. And let me summarize what we're actually doing. We're not doing a lot. We don't need a ton of information. Remember, the first value in pre-order, the pre-order array is always going to be the root, right? That's just how it works. And then once we take that value, create a node from it, and then when we try to look that value up in order traversal, right? Then we can get some subarrays, right? We can take the length of the left and right subarray. So the right subarray is 3 and the left subarray is 1 node. Now these counts 1 and 3, they tell us how to partition the pre-order traversal. So take a look at the pre-order traversal. 1 tells us that we're going to cut over here because this needs to be size 1, this needs to be size 3. And then from this subarray with only one value, we are going to recursively run the algorithm to create this left subtree. And with this subarray, we're going to recursively run the algorithm to create this subtree. And we're just going to continuously repeat that process until we get to our base cases and until we're finished with every single node that we need to create. So now let me actually show you the code. It's actually very short, less than 10 lines. Okay, so as I mentioned, this is a recursive algorithm. So we always want to start with the base case, and the base case is going to be, what if we don't have any nodes to traverse through the two arrays that we're given? That means we can return null, or basically we don't have to create a tree. So if pre-order is empty or in order is empty, then we can return null. We have no values, so we don't need to create a tree. We can return null. Otherwise, we're going to create a tree node, right? And what's the value of that tree node going to be? Well, it's going to be the first value that happens to be in the pre-order array, just like I showed you, right? Always going to be the first value, so it's always going to be index of 0. And then whatever that value was, we want to find the position of it in the in-order array. So in-order.index, so we want the index of that value, pre-order of 0. And we're going to get it in mid. Now this is the part where we're going to build the subtree. So root.left, let's create the left subtree, and we're going to do this recursively as I mentioned. So self.build tree, we're calling the function that we're inside of. And the convenient part about Python is we can do sublists, so that's going to cut down our code quite a bit. So we need to pass in the new pre-order and in-order arrays, or the subarrays more likely. So pre-order, what are we going to pass in for the left subtree of pre-order? Well, mid tells us Mid tells us how many nodes we want. The index of basically the value of mid tells us how many nodes we want in the left subtree. So what I'm going to do is for pre-order, we're going to start at index 1. We're basically skipping the 0 index because we already just created a node for the 0 index. We're starting at index 1, going all the way up until mid plus 1 in Python. This mid plus 1 is non-inclusive, so this subarray is really just a pre-order from index 1 to mid. So that's what we're doing, and we're going to pass in the in order portion that we need as well, and that's just going to be from the beginning up until mid, but not including mid, right? This probably makes more sense if you go back and look at the picture, but basically we're just creating the appropriate sublists that we need to create the left subtree. We're going to do basically the exact same thing with the right subtree. And I would encourage you to draw this out yourself to basically reinforce what you're learning or watching me do right now. So to build the right subtree, we need every value after this sublist, right? So we can just say starting at index mid plus 1, going until the end of the list. That's how you do it in Python. We're starting at mid plus 1 and going until the end of that sublist, just like I showed in the picture. And for in order, we can actually do the exact same thing. We want every node to the right of mid in order, right? From our in order array, we want every value to the right of this index mid. So we can do that with mid plus 1, starting at mid plus 1, and then going until the end of the array. So now let me close this function. And so this is literally all you have to do. The reason it's so easy is mainly because I'm using Python, but you could do this code without Python. It would probably just be a couple extra lines. You might need to pass in a couple extra parameters into this build tree function, basically just these indices that I'm doing. You might not be able to create sublists, but you can at least pass these indices into your functions in Java and other languages. So with that, we have actually created our tree, so the only thing left for us to do is return that tree. So with that being said, this is the final solution. It's probably less code than you would have predicted, but the problem is a little tricky, but it's kind of enjoyable, at least in my opinion. So I hope that this was helpful. If you enjoyed, please like and subscribe. It supports.
Interesting. That was a good video. Kind of want to draw this a little bit. You know, what I'm going to do actually is I'm going to snip this. Instead of drawing it, I'm going to snip this solution. Put it on my other monitor. Take a look at his drawing. So we start with the root, right? Because the root in pre-order is always the first value. So our root, we make a new tree node. We get our mid, right? We find our mid, which is here in our in order. Then we get our index value here, right? Which is our mid. Then we call root.left. We call the function again. But this time we pass in the pre-order from index 1, because we want to go from here, to mid plus 1. That's what I'm a little confused about here. To mid plus 1. I get the in order one. This is what I'm kind of looking at, the mid plus 1 here. That's what I don't understand. I get the in order because we're going all the way, we're getting all the values from the beginning to mid, right? Because that's our left subtree, right? So I get that. But if we're going from 1, right, we're starting from here, and we're going to mid plus 1. We're going to, what is mid? What does mid return? Mid is index 2. right? Or index 1, sorry. We're going 1 plus 1, which is 2. So we're going from 1 to 2. Why are we going mid plus 1? Well, we're going mid plus 1 because we know the length here. We want to know the length, right? Because mid plus 1 is technically the left side of the subtree, right? The length of the left side here. Plus 1, because we're indexing by 1. Which I think is correct, right? Then we call in order, and we go from the left subtree all the way to the midpoint, which is 1, the left subtree, right? Okay. And how we do root dot right? So for the right subtree, what do we want to do? We'd want to call pre-order we'd want to call the we want to go from, I think, mid plus 1 here, right, to the end. Yeah. Okay. Mid plus 1 to the end. And then okay, we're gonna construct this binary tree. I'm gonna write this code myself. Try and think about it in my way, using this as well. So first of all, we need our base case, right? So our base case is, well, if not node, if not pre-order, and not in order, right? Then we just want to return none, right? Because we're not running anything on this algorithm, right? Then we want to create our tree node, right? So tree node, what do we want to initialize it with? We want to initialize it with the 0th element in our pre-order, right? Because pre-order is guaranteed to be the root node, right? So call pre-order 0. Is that how we do it? Yeah. Sorry, we go is equal to tree or pre-order. That's what I meant. Okay, then we need to calculate our midpoint, right? Our midpoint is equal to, we need to find it in order, so we can do in order index pre-order 0, right? We gotta index our root in order, right? Then we want to loop through. We do our recursive case. We call our build tree function, right? And we pass in let's think about this. We pass in, we need our pre-order list first. So we would pass in our build our left subtree, right? This is left first, so we're building the left side, right? So how do we build the left side? Well, we need our looking at this right now, trying to kind of think about this graph. I wish I could record both screens. That'd be kind of cool. Our left node. How do we access our left node? Well, we would go passing our pre-order first. So it would be I think we'd want to go from 1 to the length of mid plus 1. How do we do this again? I think we would go the pre-order like this. I think this is how we... Alright, from 1 to mid plus 1. And then, you know, in order, our in order would go from nothing up until mid, I think. Let's double check that. Yeah, that's right. Okay. So this is our left, right? We want to build tree. We want to call our pre-order, right? And we want to build our right subtree. So how do we build our right subtree? Well, going to mid plus 1. So then we'd want to include mid. No, not include mid, because mid is our root. We'd want to go, I think, from mid plus 1 to the end. And then to our in order, where we go from mid plus 1 to the end. And then we'd want to go from is it just mid to the end? Mid plus 1 to the end. Mid plus 1 to the end. Okay. So we just missed out this part here. Okay. It's our right, and then we would want to return our root. Okay, what is wrong here? Output 3. Oh shit, I don't think we're actually returning our... This needs to be root dot left. That's what we're missing here, root dot right. Not actually adding the values. Okay. I kind of want to go through this code just to visualize it more, just to reinforce the idea. Okay, I want to reinforce the idea a little bit. So let's give me this. Okay. Okay, right. So we have our two functions, right? Let's write them. We'll do this is our man. Pre-order is equal to, we might not do the whole thing, but oh my gosh, dude. Equal to 3, 9, 2015. Three 9 2015 7. Now in order. 3, 15, 27. Okay. My God, did I get rid of the YouTube video, dude? Oh no, it's here. Okay. Alright, we got our code over on this screen, and then we got our paint. Right. So I'm going to kind of circle this stuff. Actually, no, let's just keep it, right? So we're going to create our root node every single time, right? So we start with our root node, which starts at pre-order 0, right? Which is here, which is 3, right? Then we recursively call, we calculate our mid, right? So our mid is at this point here, right? This is our mid. This is our mid here, right? So then we call root.left, and we find the pre-order of 1 to mid plus 1. So 1, not including this one, to mid plus 1, right? So that is here. It's our left subtree because to mid plus 1 is 2. And then we go from in order. We go from, this is our mid. We go to everything past mid. So everything up to mid. So, which is here, right? Then we go root.left, right? So we call root.left here. Now root.left starts at pre-order 0, right? So pre-order 0, in this case here, we only have one value, which is our first value. We put in 9, right? Okay. Then we calculate our new index. So mid is equal to in order index pre-order 0, right? Index pre-order 0, right? So we get our new index again, which is 9 again, right? Because we only have one value. So it's 9 again. And then we call root.left, right? Then we call root.left is equal to pre-order 1 to mid plus 1. Which I think in this case, 1 to mid plus 1. Hang on. Let's get GPT to run a test algorithm. Okay. Right. We got our first call in order 1 4. Is it the same algorithm? No, it's different. Damn it, bro. We have to get them the same one. Okay. Take a look at this test case, right? So call root is equal to 3, yeah. 1 2, left subtree 1 2, which is 9. Yeah. In order 1 2, which is 9 over here, right? Call left subtree root is equal to 9, in order root 9. Base case hit, no left or right children, leaf node. How does the base case hit? Root index 1 to 2 is 9, in order to 1 is 9. How was the base case hit here? No left or right children. And step 2. How is the base case hit? I don't see how the base case is hit. Left subtree. Oh, okay, right. So here we pass left subtree 1 1, which is what I said. 1 1. Right? Then right subtree 1 there, which is they get the empty string since both left and right subtrees are empty. Right? We reach this base case. If not, pre-order. And if not in order, we return none, right? So then we go back up. We check here. We go back up. Then we check. We go back to 3, right? Okay, we go back to 3, the right subtree, which is... Go back up to 3, right? So then we call the right subtree 20, 20, 15, 17, right? So let's go to orange, right? We call the right subtree, which is mid plus 1, right? For the pre-order. So mid plus 1, and we go to the end, right? And then over here we call, this is our index, we call mid plus 1 to the end as well, right? Which is this here, right? Okay. Then we would go, we would start with our 0, right? So our root is equal to pre-order 0, right? So 20. So we'd add 20 here, right? Then we calculate our mid again. Mid is equal to in order dot index pre-order 0, right? So we find 20 over here. 20 is here, right? Okay. We find 20. And then we go root dot left is equal to build tree, right? And we'll go yellow here, right? We build the tree from 20, right? And we go root dot left is equal to self dot pre-order. We go from 1, we don't count the root node, right? Go from 1 to mid plus 1. Kind of stuck here. 1 to mid plus 1. Oh no, we're looking here. We go from 1, so 9. We go from 1 to mid plus 1. 20 is our mid. We go to 1 to mid plus 1. Right, we're not looking at the whole thing because we were actually looking at a subarray, so we have to look at the subarray before. So we go from 1. Right, because we're making this smaller. This array is getting smaller and smaller and smaller because we're passing in subtrees. That's where I'm getting confused here. So we go from 1 to mid plus 1. Mid plus 1 is 2, right? So we technically get this 15, right? And then our root dot right would be, well, we go from mid plus 1 and we get 7, I think. Right, and that's where we add the left, right? So we would add 7. Don't worry about this. I know this is wrong. We would add 7, right? Oh, no, sorry. 15. And then we'd have 7, right? We'd reach the base cases here, so we'd return up the tree, right? Return all the way up back to here, and finally return our root, right? Which is our whole tree. That's how our recursive algorithm works. Holy shit, that took a long time to think about. It was definitely tough to think about, but wow, yeah. That was a tough problem for sure. Okay. Let's yeah, wow, that was definitely a really tough problem. Let's take a look at this one. Oh, man, it's something similar. Construct a binary tree from pre-order and post-order, right? So we have our pre-order, right? We have our root again. So I think it's gonna kind of go the same way, right? So we're gonna have, well, if not pre-order, sorry, or not post-order, I'm gonna return none, right? Then we're gonna always, when we have pre-order, since pre-order goes root left, right, we always take the first node, right? So we'd create our root is equal to tree node, and we'd pass in our pre-order 0, right? We know that, okay. Now we have to think about the kind of post-order, right? And post-order is, shit, what is post-order? I think it's right, is it? Man, all of them are so tough. Left, right, root. Left, right, root. So we have 4, 5, 2, 6, 7, 3, 1. We'd somehow need to calculate our mid again, right? How can we use post order in order to solve this? Our one's all the way over here though, right? I think somehow we need to get the height or something. I don't know. I don't really know. Yeah, well, look at this guy over. Okay, what do you think is the trick here? I don't know what the trick is, dude. So we get the value of the root node is the leftmost value in the pre-order array and the rightmost value in the post-order array. The value of the left child is the second most value in the pre-order array. Two values above agree, and the node must have a single child. We can then split the pre-order into the root. Take the child. The root, right?
This is your brain when you're struggling to focus.
Turn this on.
And this is your brain when you're in the zone. But getting in the zone and staying there,
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, construct binary tree from pre-order and post-order traversal. So first, before we get into it, I want to mention this is very similar to another problem that we have solved. And yes, of course, it is a Leetcode 150 problem. So if you go to the tree section, it is this problem, construct binary tree from pre-order and post-order traversal. I would recommend understanding this one before you get into today's problem. So if you look at the solution, we have pretty much like the possible solutions available here, probably in your language of choice. And I think the first solution is probably enough. And I guess the second solution as well. They are pretty similar, and they're going to be similar to today's solution. But the problem is that today's problem is actually a harder variation of the other one. So that's why I recommend solving that one first. This one is definitely harder. It's not that you can't learn anything from this problem. It's just one of those problems that, to be honest, is kind of a pain. And it's one of the problems where the constraints are kind of important. Well, I mean, they're not that important, but this one is important. The fact that all the values in here are going to be unique. They mention that here, that the values are distinct, and also that the values, mainly from this constraint and this constraint, you can tell that the values are going to be 1 through n. Of course, without any duplicates, they're going to be unique, but they're going to be 1 through n, where n is the size of the tree. So it's not a coincidence here that the values are 1 through constraint, and this constraint, you can tell here are going to be unique. They mention that here, that the values are distinct, and also that the values, mainly from this constraint and this constraint, you can tell that the values are going to be 1 through n, of course, without any duplicates. They're going to be unique, but they're going to be 1 through n, where n is the size of the tree. So it's not a coincidence here that the values are 1 through 7. So keep that in mind. One of the reasons I think this one is harder is that there actually is possible to have multiple valid trees. So the idea behind this problem is that we are given a pre-order traversal and a post-order traversal. I'll briefly mention how these traversals work, because even if you already know, it's worth walking through that and seeing how these traversals apply to this problem. I'll try to simplify it, because that's how I like to think about things, in a simple as possible way, but it's still worth walking through things in a bit more of a verbose way, especially if you're a beginner. I might not be able to do that in depth in this video, but you can do that on your own time. So the simple way to look at pre-order and post-order traversal is like this. Pre-order works like this, where we are processing the root, and then we process the left subtree. And I'm going to get rid of these brackets just to kind of save time or save space here. We have the root, indicate this, and then we have the right, which could also have multiple nodes, ... So that's how pre-order works, and then the entire right subtree. So recursively, it'd look like this: process the root once again, then left subtree recursively, and then right subtree recursively. So do the entire left subtree first, ... and then the entire right subtree first, ... and then the root. So knowing this, knowing these properties, and just to kind of run through it here on the left side, post order would be like recursively doing the entire left subtree, recursively doing the entire right subtree, and then finally doing the root. So you can see that this simplified look at it, you can see, of course, the root is going to be the first in the pre-order traversal, and it's going to be the last in the post-order traversal. Now, with this, if you want to be able to solve the problem, what you have to do is try to make a few key observations about these properties and how they can allow us to reconstruct the tree. We're just given two arrays, the pre-order traversal and the post-order traversal, in the form of an array, and we want to reconstruct the original tree. It's much harder than the other variation of this problem because we don't have an in-order traversal. That actually helps a lot. So I'm going to make some space here because I'm actually going to focus really on this example and using the pre-order and the post-order. And we're going to use those to make those observations that are going to be important. But there's one other thing that they mentioned in the problem description. There could be multiple correct trees, and that's the thing to really keep in the back of your mind. How do you deal with that ambiguity, the fact that there could be multiple solutions? This is not enough information. No matter how many observations you make from this, it's not going to tell you the exact tree. And so the question is, how can we deal with that? How can we try to simplify it for ourselves? So here is the example. Now is time to make the observation. So here is the root. This is the pre-order, by the way, and this is the post-order. So it's simple enough if we want to create our tree to figure out what the root is. So then I have my 1 over here. And the convenient thing about pre-order traversal is this. We know that the next node is actually going to be the left child, if a left child exists. Right? I mean, that's kind of what this tells us. Over here, we have the pre-order, and then we have the left. Now, you might think, okay, well, the post-order starts with the entire left subtree as well. But the problem is that the order that the post-order traversal will go through the left subtree is in reverse order. Reverse, well, not literally reverse, but kind of in reverse order from the pre-order traversal. Let me kind of
two's at the end here, right? So if two's at the end here, then you can take everything from here to this element, and then you can run a, what is, in order is left, right. come here, take this element.
Show you
I think you can do this somehow, right? So you can index this one, and somehow, like, you need to run some sort of algorithm
exactly.
to sort this into 2, 4, 5. Which maybe would be like, I don't know,
What I mean.
in
For the
order or
left
something.
Subtree pre-order is going to do this. It's going to say, okay, do 2. Great. And then do the left, which is 4. Great. There's nothing more to do. So then pop back up and then do the right subtree. 5. Great. So we did 2, 4, 5. Now the post order would do this. This is the post order for the left subtree, and this is the post order for the right subtree, and then this is the root. So the post order, you can see here, it went 4, 5, 2. So not literally in reverse order, but post order works bottom up, whereas pre-order works top down. Depending on the shape of the tree, these like values could be in a different order. But there's one thing that is actually guaranteed. What is guaranteed? Let me show you.
At the 2's
we
over
saw
here.
that this was the root, and in post order that would be over here. So let me use a different color now. We know that, like, from this information here on the right, that the left subtree is going to be contiguous in pre-order traversal, and it's going to be contiguous in the post-order traversal. So in this case, the left subtree had 3 nodes in it. So we know that the size of this chunk is going to be 3. The size of this chunk is going to be 3 as well. We don't know that, but in this example, of course, that's true, and it's going to be true for every example. We just don't know the number is going to be 3. It could be 4, it could be 5, there could be 10 nodes in the left subtree. That number is important. And how exactly do we figure out what that number is? It'd be nice for us to be able to do that. Or in other words, it would be nice for us to be able to figure out what this boundary is. Because if we could figure out what the boundary is either in this array or in this array, then we would have enough information. Because then we'd say, okay, well, we know that there's 3 nodes in this chunk, so that means there must be 3 nodes in this chunk as well. Okay, now how do you figure out that information? Which observation is going to help us figure that out? Well, I actually pretty much went through it. Remember, pre-order works top-down. Post-order works bottom-up. We know that 2, if there is a left child of 1, 2 is going to be that left child. We also know that wherever this 2 happens to be in the post-order array, it happens to be over here. Well, post-order says that this will be the last node traversed in the left subtree. So that tells me that this was the last node to be traversed, and thus everything that came before it also belonged to the left subtree. We don't necessarily know like the positions and all that, but this is how you figure out the boundary. Let me restate it. We know that 2 was the left child, and thus if we can figure out which position, if we can perform some kind of lookup to figure out which position that value was in the post-order array, then we figured out the boundary, we figured out the distance, and this will allow us to solve the problem recursively, because now we have a chance to be able to break this down into sub-problems. Now we can somehow maybe take like this chunk over here, this chunk over here, and then pass it into a recursive function where we then, instead of trying to build the entire tree, we broke it up into a sub-problem where now we are going to try to build the left subtree. And if you're paying attention, you'll probably know how to build the right subtree as well, because look what I did over here. I already said this is the root, this is the root, this is the left, this is the left. So I know that everything that's left over here in pre-order and here in post-order, that can be supplied to build the right subtree. So those are more or less the observations to make to arrive at a working solution. But there's one thing I kind of glossed over. And don't worry, I'm going to walk you through like some of the implementation details for this.
I'm going to go back a little
Instead
bit.
of trying to build the entire tree, we broke it up into a sub-problem where now we are going to try to build the left subtree. And if you're paying attention, you'll probably know how to build the right subtree as well, because look what I did over here. I already said this is the root, this is the root, this is the left, this is the left. So
That's the right,
I
so
know
you-
that everything that's left over here in pre-order and here in post-order, that can be supplied to build the right subtree. So those are more or less the observations to make to arrive at a working solution. But there's one thing I kind of glossed over. And don't worry, I'm going to walk you through like some of the implementation details for this. I think that's mostly better covered in the code anyway, but there's one very important thing that's not an implementation detail, that's more about just the solution in general, which is this. I mentioned that we know this is the root over here, and if it has a left child, the next value will be the left child. But how do we know? Like, that's where the ambiguity comes in. What if we had something like this, where let's say these values just didn't exist. Let's say these values that were in the right subtree, they just didn't exist. And so let's say that this was the tree that we were trying to build. 1, it has 2 on the left side, and then, you know, that whole subtree. Okay, in that case, our assumption that this node was the left child, that was great. That actually did work. But what if our assumption was wrong? What if instead this entire subtree was not on the left side and it was actually on the right side? We had a 2, and then we had like a 4 as the left child, and then we had a 5 as the right child, and this is just a subtree on the right side of 1. Well, in that case, we will have built the wrong tree, but it's actually okay for us to do that, because they didn't tell us we had to build the exact correct tree. Because in this case, it's actually ambiguous. There is no correct tree. This technically follows the traversals that we were given, and the other tree also follows that as well, like if we had this. So if we don't know, then we just assume that whatever we're looking at is on the left side. And if there happens to be additional nodes, well, that's okay, because we'll have space on the right side for those nodes as well. So that's why we choose to put them on the left side. If you wanted to, you could do it the other way. You could put this on the right side. That's assuming that there weren't like 2 subtrees, but it's easier just to implement it by putting it on the left side. Because then if there are 2 subtrees, then we can put one on the left side and then one on the right side. I hope that makes sense. Now let me try to kind of walk you through a little bit of the implementation details. It's mainly going to be a matter of like manipulating the pointers. I'm not super creative, so what I'm going to say is I'm going to have, let's say, I1, which is going to be at the beginning of pre-order, and I2, and then I'm going to have J1 and J2 for the other array. Conceptually, this is how it's going to work. Like, it's going to say, okay, we're trying to take this pre-order and this post-order and create a tree out of them. So we know that, okay, we can take the first one in the pre-order. That will be our node. That will be the root. And now we're trying to build the subtrees. For the left subtree, we're going to say, okay, is there one more node in the pre-order traversal? If there is, then we'll say that that's going to be the left child. If there weren't anything here in the first place, well, then we would just stop and we would return this node. But there is, so then we say, okay, I have my guy over here, and then I want to perform a lookup so I can figure out which index it's in the post order array. Now, how do I perform that lookup? The easiest way would just be to dump all of these values, throw them into something like a hash map, or you could actually also use an array, because we know that the values are going to be a continuous from 1 through n, but a hash map is enough. That will tell us the index of every value, so we'll be able to look, and we'll say that that's going to be the left child. If there weren't anything here in the first place, well, then we would just stop and we would return this node. But there is, so then we say, okay, I have my guy over here, and then I want to perform a lookup so I can figure out which index it's in the post order array. Now, how do I perform that lookup? The easiest way would just be to dump all of these values, throw them into something like a hash map, or you could actually also use an array, because we know that the values are going to be a continuous from 1 through n, but a hash map is enough. That will tell us the index of every value, so we'll be able to look that up. We'll see that the index is over here. That tells us the boundary, so I guess I can call that like mid, but in any case, what we're going to do is take this part from J1 all the way up until mid, and then pass that in recursively to the left call. Now, how would we know how many values to get from here? Well, we could just get the distance of this. We see that there's 3 values, so then the distance from here should also be 3, and thus we can say that the boundary would be over here. And wherever that boundary is, then we can say, okay, well, everything to the right of that, all the way up until I2, is going to be passed in to the right subtree. And similarly over here, everything after the middle pointer, which is going to go there, up until but not including J2, is going to be passed in to the right subtree there. And whatever these subtrees happen to build will then be assigned to the left and right pointers of the node that we created, the root node. So is this easy? I definitely don't think so. In my humble opinion, this is actually more difficult than the problem that we solved yesterday, which was technically a Leetcode hard. That's why I don't really care too much about the difficulties that are assigned to these problems, because it's very arbitrary. Maybe some of you find this problem easier, that's fine, but I think it's very subjective. Now, the fact that our lookup is like a constant time lookup, that does mean that this solution will actually be a linear time solution, and I believe linear space because it's going to be recursive, so the recursive call stack will take up some space as well. But now I think this is enough to get into the code. And actually, I guess I could take like a few more seconds to quickly just dry run through this, or at least I'll dry run through like the left subtree, how that's going to be built. So right now we're here and we're here. So once again, we are going to take the first node that's in the pre-order, that's 2. We're going to create a node here. We're going to look up where 2 happens to be, or actually, we're not going to look up 2. We're going to look at the next node, which is a 4. We're going to look up where is 4. It's over there. So that tells us the boundary, meaning that 4 is going to be passed in to the left recursive call. And since there's just a single node, that's kind of like the base case. And everything that comes after, which is just 5, is going to be passed in to the right side. And we know that that's over here. 5 is just a single number. The reason we know that we can stop here is because the distance here is 1. The distance there was also 1. And so then we're going to end up here on the left side with a tree that looks like this, 4 on the left side and 5 on the right side. So you can see that it does work. Then we pretty much ran out of values here in the left subtree. So then we would build the right subtree. It would end up pretty similar. I encourage you to walk through that if you're still unclear on how this works, or maybe wait until I code it up and then try to walk through the code. If you want to know what my thought process was, here it is, but I don't know how helpful it's going to be for you. First, I'm going to just get the length of one of these inputs. They're both going to have the same length, but then I'm going to create a hash map for them. I guess I'll call it post-val to index.
Okay, we create a length n. Which can be either, right? We create a hash map. So dict is equal to counter post order.
It'll map each value in the post order to the index of that value. And we can build it like this, in enumerate.
Oh, this is going to count though. We don't want to count.
Array, and
we don't want to count, right? So we'll build our hashy. Are you in? That's no dick.
here's that. So now that we have that, we can implement
post-val fix. Value. Oh shit.
our recursive function, which I'm going to call build. It'll take 4 pointers, I1, I2, which will tell us which portion of the pre-order array that we're currently looking at, as well as J1, J2, which tell us which portion of the post-order array that we're looking at. And so the way this function is going to be called, it's not really a surprise. tries, we're just going to call build, going from 0 up until n minus 1 and 0 n minus 1. So there's many ways to like code this up, and there's many like little things you can do to simplify the code. I might do those towards the end, like the simplifications, but for now I'm just going to kind of start with like the basic thing. What we want to do is first just create a tree node. Take the first value in pre-order, which we can get with our pointer I1, and create a node out of it. Let's call this the root. Now, what if it was possible actually that the portion that we're looking at is empty? That's going to happen eventually. Like that's going to be the base case where we can't actually create a node. We can't just infinitely keep creating nodes. So I think that case could be handled like this if like one pointer crosses the other, but I'm actually not even 100% sure if this is going to happen. I'm going to leave this as is and maybe simplify it towards the end. So that could happen, or maybe J1 could cross the other pointer. In that case, we'd want to return, and we can return null. Okay, so we created the root. This is what we want to end up returning, but we just don't know if we have to create a left and right subtree for this node. We can check that like this. If I1 is not equal to I2, then we have to create some subtrees. Maybe 1, maybe 2. But either way, we need this to be true, because if I1 and I2 are equal, that means we only had one node. We already created that node, and now we can return it. So that's why we would skip this if this weren't true. But anyways, now we are going to build the left subtree. So we know that the left value is going to be this. It's going to be the next value in the pre-order traversal, like this. So at I1 plus 1. Okay, now I want to get my mid pointer, what I talked about earlier, which is going to tell me the boundary in the post-order traversal. And I can get that with my hash map that I created, post value to index. So I do this, post value to index. I take that left value I just computed, and let me call this mid. Okay, now using this mid pointer, I'm going to get the size of the left subtree. So I'm going to call that left size, and it's going to be mid minus J1. Because remember, mid is the pointer for the post-order traversal. J1 is the beginning of the post-order traversal. And so the difference will be the size, but we need to offset this with a +1. So that will be the true size. Now is the time to build the subtrees. So we will build the left subtree and then assign the result of that to root.left. How are we going to do it? Well, the starting point is going to be I1 plus 1 for the pre-order traversal, I1 plus 1. And I'm not quite sure right now, like at the top of my head, what is going to be the ending of the pre-order traversal. Well, I am, but I'd like to fill these in easiest to hardest. So we know that the post-order traversal is just going to be J1, and it's going to end at mid. So that tells us the post-order traversal part. The pre-order part is going to be from I1 plus 1 up until some point, which we can get with the size, because we know that the size of this portion should be equal to the size of this portion. So we can get that by just taking I1 and adding the size to it. So I will do I1 plus left size. You might think, well, why didn't I need to do like a +1 or a -1? And that's a question I'll let you try to answer on your own, because it's literally just a math question that's not really related to trees anyway. I'm pretty sure you'll be able to figure that one out. Now we can also try to build the right subtree. So we'll do this. Root.right is going to be equal to build this. So everything else, everything to the right of this is going to be passed in to the right call. So this was the ending of the pre-order portion. So we want to start one spot after that. So we can copy this and then do a +1. And then this is going to go all the way up until the end of the pre-order portion, which is just I2. So I'm going to put I2 right there. And for the post-order portion, it ended at mid, so it should start at mid +1, and then it'll go all the way up until the end, but we didn't include the end, like the last element. That was pretty much what the root is, so we'll do J2 minus 1. That's technically correct. So I think this code is actually complete. This is the entire code. I do believe it'll work. There are some minor simplifications that we can make to it. Let me run it first. Okay, very, very sloppy bug on my part. I don't know why I had index here. It should just be I. Sorry about that. But now you can see that this code does work and it is pretty efficient, though be able to figure that one.
Bro, like, dude, I don't understand like what he's doing in this part of it. Like bro, what? I1 is less than I2 or J1 is greater than J2. Turn none. Passing the root is equal to tree node. Pre-order I1, right? So we're looking at the first value. I1 does not equal I2, so it's more than one node. We go left val is equal to pre-order I1 plus 1. Find our mid value, right? Minus codic. Left val. Left size is equal to mid minus J1 plus 1. I root dot left, and then we recursively call I1 plus 1. I1 plus left size. J1 mid. Root dot right is equal to build I1 plus left size plus 1. I2 mid plus 1. J2 minus 1. We return our root.
This code is actually complete. This is the entire code. I do believe it'll work. There are some minor simplifications that we can make to it. Let me
Oh, whoops, we didn't call our function actually.
run it first. Okay, very, very sloppy bug on my part. I don't know why I had
Okay.
index here. It should just be I. Sorry about that. But now you can see that
Whoops. Print. Right, prints the value. Okay, we go from I2 to I1 to J2, right? Passing our root, which is always our first value, right? Our I1 starts at 0, right? If I1 does not equal I2, I2 is equal to a minus 1, right? find 2 in here, right, which is here. Then we call left size mid minus j plus. The value's in the mid. Okay, yeah. Then we pass in our thing. Okay. I understand. Okay. Interesting way to think about it. Again, I probably wouldn't have got that. I'm just trying to get that intuition is the main thing. But I actually realized that I have to go. It's gone so quick, I feel like, this video. I mean, we've been going for about an hour and a half now. So anyway, appreciate you guys watching. I will not see you tomorrow, but I will make a video on Sunday. I'll be back on Sunday. So I'll see you guys on Sunday. See you guys later.